Okay, let's talk a little bit about the z-score equation and how the solutions manual will change it up every time. But the general idea for the z-score is that your sample minus your mean divided by your standard deviation. Now, this is going to look different in every chapter. When we did it in chapter 6, it was x minus mu over sigma. Okay. But we don't really have mu and sigma in chapter 18. In chapter 18, your x is the proportion that it asked you about. What's the probability that it's less than 10%? That is your p hat. Your sample minus the proportion of the population. P hat is your sample proportion. P is your population proportion. And your standard deviation is not sigma, it's the square root of PQ over N. But instead, I don't tend to use every different formula because it's going to change with every single chapter. Every unit, it's going to change. We have to know the general idea. What did it ask us for? That's your sample. Minus what did it give you? What is the proportion for the population divided by your standard deviation? And that's going to look different in every chapter. Caleb.
So Q is classified as like the given percent?
P is the given percent. Q is 1 minus P. Q is 1 minus P. Okay. So our formulas are going to morph a little bit in every chapter, and I feel like it gets confusing once we get into the 2 sample chapters, and so I usually just write it in general. So with chapter 18, our normal model is P, comma, PQ over N. That's your mu and your sigma. So number 13, let's look at it. It is generally believed that nearsightedness affects about 12% of all children. That means P is 0.12. What is given to you in the problem, that is the population proportion. A school district has registered 170 incoming kindergartens. There's your N. 170 kindergartners. Can we apply the central limit theorem to describe the sampling distribution model for the sample proportion of children who are nearsighted? Check the conditions. So for A, we need to check conditions. Now, yeah.
If it doesn't say exactly that it's random, are we supposed to assume that it's random?
I'm going to talk about that right now. What do we do if it doesn't say it's a random sample? Okay, this school is not, you guys, there's way too many side conversations. This school is not getting a random sample of kindergartners, right? We don't get to randomly choose our students. They come to us because of where they live, okay? So if we cannot say it's a random sample, can we say that the students in this kindergarten class are most likely representative of all of the students that are going to come into kindergarten? Yes, right? Those 5-year-olds are pretty representative of next year's 5-year-olds, and then the next year's 5-year-olds, or last year's 5-year-olds. There's nothing that's, you're looking at this one school, and the school pulls from the community, and so your grade level is pretty representative of the community. So I can't say it's a random sample, but I can say it's likely representative, okay? So the sample of kindergartners is representative. Now, you only say it's representative if it doesn't say it was a random sample. I have students all the time, it says random sample, and they're like, oh, it's representative. No, it's a random sample. If it's a random sample, that's better than it being representative in our opinion. So the representative statement is only our fallback if we cannot say it's a random sample. Okay? So that's what we're going to say because we don't have a random sample. And there's a lot of situations where we can say it's representative, and then there's some that we can't. If we're looking at the GPA of the school and we used this classroom as a sample, this classroom is not representative of the entire school's GPA. This is an AP math class. Every month, one of our students becomes student of the month from this class almost. This class is not representative of the school's 12th graders, right? You guys are the cream of the crop. So we can't say that that's representative if that were our case. So you have to stop and think about, is that reasonable to say that it's representative? That 170 is less than 10%. Now, these are all this year's 10th graders, right? So it's clearly not less than kindergartners. It's clearly not less than 10% of this year's kindergartners, but is it less than 10% of what they're going to have past, present, and future? Yes. Okay. We are choosing this year basically to get the data, and we're trying to estimate that for other years, so there's going to be lots of kindergartners coming in and out, definitely more than 1,700 in the next couple decades. So it's okay to say it's less than 10% of all potential kindergartners. We're just going to write kinders because I'm lazy. And then so when we talk about independence, we don't necessarily need to write it down. It's not one that the AP exam requires you to write down, but your book always will. Is it reasonable to say that each child's nearsightedness is independent of the next child? Absolutely, right? Even if they're siblings, I have one kid that needs glasses and the other kid doesn't, right? So even siblings, although it's more likely that one will need them if the other, your eyesight is independent of the next kindergartner in the school, right? So independence is reasonable. And then we check our NP greater than equal to 10 and NQ greater than equal to 10. So that's 170 times 0.12 and 170 times 0.88 and 20.4. Yes, I know that you cannot have 20.4 kindergartners. But what we're saying is we would expect an average of 20.4 kindergartners to be nearsighted. And then 170 times 0.08 is 149.6. You have to write down that number. Okay? You can't just leave it as 170 times 0.12 and then not write the 20.4. Stupid mask. Okay. So, we need to say, okay, we have to answer the question. The question was, can we apply the central limit theorem to use a normal model, basically? So, since conditions are met, you're going to get really tired of this sentence. But it's really important that you understand why you are checking the conditions. Since conditions are met, a normal model is appropriate. Now, there will be times when the conditions are not met. And if conditions are not met, then we cannot use the normal model to do these calculations, and we have to find another way. Okay? Now, thinking about this in a real world setting, when you are going to do an experiment, okay, we are checking the conditions after the fact. The experiment, the study has been done. Did they meet the conditions? If you're conducting an experiment, as you set it up, you have to make sure that you're meeting the conditions that are necessary. Is my sample less than 10% of the population? Okay. If Elsinore High School has a population of 2,000 students, our sample should not be more than what? 200, right? It needs to be 200 or less to meet the 10% condition. I need to make sure that my sample is randomized properly. Okay? Think about your response bias projects. You had to make sure that as you were doing your experiment and your surveys, you were meeting those conditions. Okay? Now, we didn't make you ask 100 people, right? Because that would have taken forever. And then you want to make sure when you pick your sample size, if you have an idea about what percentage might answer yes or no, then you make sure that you expect at least 10 people to answer yes and no to each question. That's the success failure. If you don't know, then you assume 50%. Okay? So in the real world application, you're not checking the conditions after the fact. You're using the conditions to help you design your experiment to make sure once you get your final results, you can use the hypothesis testing that's necessary to determine if your results are significant. Okay? So conditions are met. Let's look at letter B. So letter B says sketch the normal, the sampling model. So my model is normal. My mean is 0.12. And my standard deviation is 0.12 times 0.88 divided by 170. And 0.12 comma 0.025. So my normal model starts at 0.12, 0.145, 0.17, 0.195, yeah, 0.095, 0.07, 0.045, yeah? That's 99.7. Here's your 95. And here's your 68. Okay. So, next question. How many of the incoming students might the school expect to be nearsighted? Well, on average, we expect 20.4. That's your NP, right? But 68% of the time, and it says how many students, right? Not what percent. Yeah. So 95% of the time, 0.07 times 170 is 12. So between 12 and 29 students, they expect to be nearsighted.
So all conditions have to be met for the normal model to be appropriate.
Correct.
So it's not, if like one condition wasn't met, then it wouldn't be appropriate.
Correct. If one condition is not met, then the normal model is not appropriate, and you can't, these calculations are not correct. Okay?
So then in that case, I would just write that since conditions are not met, a normal model is not appropriate?
Yes, exactly. Since conditions are not met, a normal model is not appropriate. That's what you would write if one of your conditions is not met. Because I think there was a problem that said, just asked you about conditions being met. So you can't use a normal model. You could possibly use the binomial model in this situation because it is success failure. It's a Bernoulli trial. Do you have to go and do that? No. Okay. Okay, you asked about how to find if it's less than 10%. So let's do number 15. Based on past experience, a bank believes that 7% of people who receive loans will not make payments on that loan. 7% of people who receive loans will not make payments on time. The bank has recently approved 200 loans. What are the mean and standard deviation of the proportion of clients in this group who may not make timely payments? So the mean is 0.07. The mean of the sampling distribution for the proportion is the proportion. Okay, so the mean is the proportion. On average, they expect 7% to not make their payment on time. So it doesn't seem like it's a mean because we're not used to means being proportions. But that's the average percentage we expect to not make the payment on time. So that's the mean. The standard deviation is the square root of 0.07 times 0.93 divided by 200. So it's a normal model, 0.07, 0.018. That's how you can write the shape, the center, and the spread. Now, we didn't check conditions yet. What assumptions underlie your model? Are the conditions met? Well, the assumptions are that each person's repayment of the loan is independent, right? Which is pretty safe to say. Is it a random sample? No. But is it probably representative of the people they give loans to? Yes, right? So we can say representative of people the bank loans to. 200 is definitely less than 10% of all loans they will give out. And 200 times 0.07 is 14. And 200 times 0.93 is 186. So the assumption is that the sample size is large enough. That's our assumption. And we check the NP and NQ condition to make sure that that is a reasonable assumption. The assumption that it's independent, we check to see if it's representative and if it's less than 10%. Okay, so we have the assumptions of independence and sample size large enough, and then we use the conditions to check to see if it's reasonable to say, yes, we're going to assume independence. Yes, we're going to assume the sample size is large enough. So yes, those conditions are met. What's the probability that over 10%, well, not X, in this case it's P hat, is greater than 10%? What's the probability that in these 200 loans, more than 10% of the people don't make their payment on time? So that's where we go to the z-score calculation. Okay? In the next rest of the semester, if it is asking you for a percent, it is asking you for a z-score and a normal CDF. Okay? Yep. Yes, I can. Okay, let's write out the z-score calculation. 0.10 minus 0.07 divided by 0.018. Remember that we don't mix those formulas I gave you yesterday. We're talking about proportions, so our standard deviation is square root of PQ over N. I don't take that and put it in the other equation. I only use the other equation when they tell me what sigma is. Okay? And so this, I need this number. Let's open a little video of the calculator. Okay, so it's 0.1 minus 0.07 divided by 0.018. So my z-score is 1.667. Normal CDF, second, right here. Distribution is in the VARS button, down to normal CDF. Now this asked for greater than, more than 10%, So it's my z-score, comma, 99. So my z-score is first. I'm going to use second answer. And then I'm going to put 99 for my upper. Or you can type in 1.67. And then we hit paste. And then we hit enter. So this is 1.667. And we write out normal CDF. 1.667, comma 99. So there is a 4.78% chance that over 10% of those 200 people do not make their payments on time. What? No. 4.78%. Right? 4.78% chance. Decimal point moves twice. 19 says, based on the 74% national retention rate described in exercise 17.74, does a college where, so P hat, the sample from this college is 522 over 603. Does this college, where 522 of the 603 freshmen return the next year as sophomores, have a right to brag that it has an unusually high retention rate? What can we calculate to determine if this is unusually high? The z-score, right? In order to do the z-score, I need my standard deviation. So we need to, the standard deviation is not based on p hat here, it's based on p. So it's the square root of 0.74, 0.26. What's my sample size? Nope. 603. Come on, guys, the denominator is out of how many, right? So the top is how many freshmen returned. 603 is how many there were total in the freshman year. 0.74 times 0.26 divided by 603 is 0.0179. And then 522 divided by 603 is 0.866. Okay. So what's my z-score calculation? 0.866 minus 0.74 divided by 0.0179. I'm assuming you actually checked conditions in number 17, right? Because otherwise, if it just asks this information and I don't check my conditions, I've just lost points. When I do quizzes and tests, checking conditions are worth 4 points. 1 for the random, 1 for the 10%, 1 for the NP and NQ, and 1 for the since conditions are met, a normal model is appropriate. You have to check all those things. So if the problem is worth 6 points, the conditions are worth more than the calculations. You have to check your conditions. But you did that in part 17. So I got 7.039. Is it reasonable to say that if a school's retention rate has a z-score of 7, it's unusually high? Yes. 7 standard deviations above the mean, which is unusual because anything above 2 standard deviations above the mean only has a 2.5% chance of happening. Okay, so yes, and here's the thing. Did I answer the question by writing 7.039? No, I did not answer the question. I need to say yes, it is unusually high because it has a z-score of 7.039. When I do the normal CDF, what just happened? I get 9.7379 E negative 13. You have to pay attention. Hold on, let me put a picture of this in here real quick. I want you to see what the calculator looks like. So there's my z-score calculation. So here's my z-score. It's really important you pay attention to this part. When you do normal CDF, guys, this is really important because people leave this off all the time and their answer makes no sense. You cannot say that the answer is 9.74. It's not. It's times 10 to the negative 13, which is really, 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 really small. Yes, 13 times to the left. Okay? I didn't count to make sure that was actually 13 zeros, but that's what that means. So if you get an answer above 1 from normal CDF, it should have the E next to it because probability is between 0 and 1. Okay? Okay, so groovy M&Ms are supposed to make up 30% of candy sold. We talked about these groovy M&Ms in a previous problem. In a large bag of 250 M&Ms, what is the probability we get at least 25% of them that are these groovy speckled candies? So what's the probability that P hat is greater than or equal to 0.25? That's the question. Oh, wow, she actually was like, a situation is called a Bernoulli Trial if it meets the following. Wow, I'm impressed, Siri. P is 0.3, so what is my standard deviation? How do I calculate standard deviation? Is it given to me? No, I have to calculate it. 0.3 times 0.7. And what's my sample size? 250. Okay, so 0.3 times 0.7 divided by 250 is 0.029, we'll just say. So my z-score calculation is 0.25. Now, what did I forget? What have I not done? Conditions. I started calculating before I checked my conditions, and I don't know if they're appropriate yet. My calculations will work. So, is that large bag of M&Ms a random sample? Probably not. I'm guaranteeing you that if I bring in M&Ms for something in class, I am not randomly labeling all of the M&Ms in the store and then randomly choosing a bag. I'm just grabbing, right? Assuming that that bag is no different than the rest of the bags, right? There's nothing special about it. It's representative. Again, we use representative a lot, okay? So the bag of M&Ms is representative. 250 is less than 10% of all M&Ms. Right, of all M&Ms in the world. Yes, that's good. And 250 times 0.3 is 75. And 250 times 0.7 is 175, right? So since conditions are met, a normal model is appropriate. Whatever. Now I can go back and do my calculations. 0.25 minus 0.3 divided by 0.029. So 0.25 minus 0.3, so that's 0.05 negative, divided by 0.029, negative 1.724. I'm going to do normal CDF, negative 1.724, comma 99. My z-score is negative. Why didn't I do less than? Why didn't I do negative 99? Right. The question is at least, which means more than 25%. So what I do in normal CDF is determined by what the question asked me for. And
So if it was less than, would it be negative 99?
yes, if it asks for what's the probability I get less than 25%, I would use negative 99, comma, negative 1.7, negative 1.724. So I get 0.957. So there's a 95.7% chance of getting at least 25% groovy M&Ms.